Hello, my name is Andrew Zhao, and today I will be talking to you about something known as transparent conducting oxides. Transparent conducting oxides are a fascinating material which have many unique characteristics, such as the ability to be both conductive and transparent at the same time. I also believe it can be a possible solution to one of the world's biggest problems, which is climate. Its current climate crisis. And in 2018 alone, 89% of our world's carbon emissions originated from carbon dioxide. And I believe that renewable energy can be one of the biggest uh, abilities to solve this current crisis if it becomes competitive with traditional energy. And I believe another possible solution may also be something known as a smart window. A smart window is a piece of technology that allows us to change the color of windows, which may save energy consumption from traditional heat, ventilation, and cooling systems. And transparent conducting oxides are also a relatively new type of technologies, so they do have many drawbacks. And here's a little background information on transparent conducting oxides. Transparent conducting oxides are a type of heavily doped semiconductors, which are used in many everyday appliances and in the future could hold many uses in many other types of applications. For example, they're used in smart windows, flat panel displays, and touchscreen devices. And semiconductors are unique because they allow for the control of energy, which allows it to have uses in technologies such as computers. And semiconductors are generally doped, which means that they either have an extra electron added, which makes them negatively charged, therefore n-doped, or they have an, a hole, which means it's missing an electron, which therefore makes it positively doped or p-doped. And TCOs are just basically a type of semiconductor, but they're doped heavily and usually it's a metal or metally doped with a non-metal substance. For example, one type of TCO that we use often is something called indium tin oxide, which is also known as ITO, and it's basically just indium doped with a non-metal, which is oxygen. And in order for a semiconductor to qualify as a TCO, it must have a band gap of over 3.2 eV. And band gap is basically the amount of energy needed to excite an electron. And basically, a higher band gap means that it takes more energy for a particle to pass through, which generally means that if it doesn't have as much energy as the band gap, it just passes right through, making it transparent. And solar panels are a type of technology that can be used to generate electricity. And basically, solar cells use semiconductors to generate electricity. This is done through using the photon that gets released in the sun to pass through to the middle of the semiconductor layer, which is known as the p-n junction. And when this photon hits an electron, it knocks it out of place, which creates a hole, which causes the electron to rise and to be collected by this metal slab at the top, and for the hole to go to the bottom, which is then collected at an aluminum layer at the bottom. And then the electron passes through the metal slab into this wire and comes back and rejoins the semiconductor in the hole. However, if you notice, there is a slight design flaw in solar panels, which is the fact that the metal slab at the top, which collects electrons, is actually not transparent because metal is not transparent. This means that we need to find a workaround to this problem. And currently the workaround is to use grid-like patterns as shown in this image, which basically allows some part to let light through and other parts to not. And this may seem like a working solution. However, there are many problems with this, which is the fact that some parts actually don't reach the metal because it's too far from it, which therefore makes solar panels not have a 100% efficiency rate. So this is when something known as a transparent conducting oxide comes in. As you can see from this image, which is an example of a type of solar panel that uses TCO technology, rather than having the metal buffer layer, it uses transparent conducting oxide, which allows light to pass right through it and reach the active material in the middle, which is the semiconductor composite layer. And generally, this is already been done by some companies. For example, the Center of Renewable Energy Systems Technology used magnesium doped zinc oxide as a buffer layer instead of metal, and when deposited was a type of technology known as magnetron sputtering. It was able to result in an efficiency of 12.5%. And while this is decent, it's not good enough because currently the average solar cell efficiency ranges somewhere from 15 to 20%. However, Another study used indium zinc oxide as a buffer layer, and it resulted in a 26.7% improvement. And another technology that I talked about was smart windows. And smart windows allow the brightness of windows to be adjusted, which can lessen the amount of electricity that we spend on HVAC systems. And what this means is that we can use smart windows to change the opaqueness of the window. So there are many ways to implement this type of technology, and one of these is to use suspended particle devices, which are an interesting solution because they, in a way, they kind of act like curtains. They work by using transparent conducting oxide material to kind of send a charge, which causes the suspended particle devices to kind of like line up and not like lie through because they are magnetic and they send like a magnetic force through. And when the voltage is released, the magnetic force disappears, which causes them to scatter again, which, as you can see from this image, allows light to go through again. And this is only one type of solution. Another type of way to implement TCOs into smart windows is to actually use something known as the electrochromic window, which is basically just a normal window, except on top there's a special coating, which once electricity is passed through a TCO material, it actually reacts with the material, which causes it to change colors. And it can also change back colors. However, while this might sound great, TCLs aren't actually, they do perfect and they have many problems. And one of these such problems is scarcity. And basically, indium tin oxide, the TCL that we generally use the most in everyday technologies right now, is actually very hard to produce. Well, it's not hard to produce, but the manner of producing is very much of a hassle because it doesn't actually appear in the wild. And in order to produce it, it's actually made as a byproduct of processing zinc. And this alone has basically caused the price of it to rise 800% in 2002. However, this may not be true because in more recent times, there's actually been over 5,700 tons of it in reserve, which probably most likely will not be used up in the next few decades. And another thing to take into account is TCLs aren't actually a perfect material by itself. Like they aren't flexible, they lack the conductivity of metal and aren't as transparent as other insulators. However, this basically means that we may be to use different types of materials such as graphene, which is basically just a very thin layer of graphite, basically one atom thick. However, this is not very cost viable, and we really don't have any means of producing it commercially because in fact, one of the only ways that scientists have managed to produce it is to basically just put a piece of tape on graphite and just pray that it results in some graphene. So I believe that TCLs are still the best solution. And basically, this is what transparent conducting oxides are and how they may help our environment in the future.